In this video, we're going to discuss the different types and classes of polyunsaturated hydrocarbons. Before we get there, we're going to go back over some naming conventions just because it's been a while. So you might not recall all the naming rules for double bonds. So remember that you still have to find the longest carbon chain, but that carbon chain must include any of your multiple bonds that you have. So if you have a branch structure and you have a longer chain that does not include the alkene, you're not actually going to use that chain. You're going to use the one that includes the alkene. None of these examples have that happening though. So this first molecule is 1, 2, 3 carbons long. So it is going to have prop as its prefix. Also, there are 2 alkenes, and remember that we use the prefix di when there are 2 of something. So the name of this molecule is 1, 2 propadiene. So what we're saying with this name is that there are 2 alkenes in this molecule. It is 3 carbons long. And the 1, 2 indicates that one of the alkenes starts on carbon number 1 and the other one starts on carbon number 2. So 1, 2 propadiene. This molecule also has a common name, which you're welcome to use and I encourage, which is allene. In the next molecule, we've actually looked at this one already and used the name in the previous video. We just didn't really talk about where the name came from. So this carbon chain is 4 carbons long. It is also a diene, and the bonds start on carbons 1 and 3. So this is 1, 3 butadiene. You can also write buta 1, 3 diene if you would like. Sometimes the numbers need to go into the middle of the name in case you have a lot of other things on the molecule. This is not an example of that, but remember that that is an option, that you can always put the numbers right next to the part of the name that you're indicating. In this next molecule, we have a couple things that we need to think about. So first of all, we have a diene. We need to also indicate the directionality of this bond. So let's go ahead and number. We have 1, 2, 3, 4, 5. So the base of our name is 1, 3 pentadiene or penta 1, 3 diene. And then we also need to address the fact that this double bond is in the cis position. Remember that you can use the EZ nomenclature or you can use cis-trans. But remember that cis-trans is not always applicable. So here you could actually call it cis 1, 3 pentadiene or penta 1, 3 diene. But you could also say 3Z penta 1, 3 diene. So both ways are accurate. Using E and Z is never wrong. Sometimes cis and trans can be wrong. So in the next one, we have an alkene and an alkyne. So we have to think real fast, what is the priority? Because that's going to tell us from which direction we need to start numbering. If you recall, the alkene is actually the higher priority than the alkyne. So we're going to start numbering from the right-hand side. And remember that there are 2 carbons here. That's one of the more common mistakes made when naming alkynes, is that students just tend to lose carbons. So this is a 5 carbon structure, so our prefix is pent. And this is a perfect example of needing to insert the number into the name. The easiest way to name this is going to be to say 1 ene 4 ine. Because if you said 1, 4 pentenine, that's a little less clear. And the purpose of IUPAC is to always be as clear as possible. So you could describe a molecule to somebody, you know, doing chemistry in China or Russia, and we would all come up with the same names. In the next one, it doesn't matter which side we start numbering from because the alkenes start in the same place no matter what. This one we also are going to need to indicate directionality. Notice that in the ones where we did not indicate cis, trans, EZ, it's because each of the carbons or each of the alkenes had a CH2 as part of it, and that's going to prevent us from having any, you know, cis, trans. But in this one, the alkenes each have one substitution on each carbon, so we do have to indicate cis and trans or EZ. In this case, both alkenes are trans or E. So the base of our name here is 2,4-hexadiene, but we could indicate 2E, 4E, 2,4-hexadiene, or you can write trans, 2,4-hexadiene. Also recall that commas are used to separate words or to separate numbers, and hyphens are used to separate words from numbers. So if you are putting a punctuation between two things that are the same, so two words or two numbers, you use a comma. If you're putting a punctuation between two different things, so words versus numbers, you need to use the hyphen. Okay, and then last two examples involve cyclic alkenes. So these are named in exactly the same way. You're still going to have to use numbers to indicate where the alkenes are and such, but you also have to throw in the prefix cyclo. So we would start numbering from one of the alkenes. Just make sure that you choose the numbering scheme that's going to give you the lowest overall numbers. 1, 2, 3, 4, 5, 6. So we need to use cyclohexadiene as the base of our name, and our numbers are 1, 3. And I think the biggest mistake that I tend to see on naming these is that students will remember the di or the cyclo, but sometimes not both. So make sure that you are naming everything about the molecule. And then in the next one, it's almost an identical name. It's just your numbers are different. So 1,4-cyclohexadiene. If you are one of the types of people who struggle with getting all the pieces of the name, maybe try listing out the pieces if you aren't able to just spit out cyclohexadiene, which is definitely reasonable because you haven't been taking organic chemistry for that long and you don't often name things. You know, just write down the pieces that you see. So you could say, okay, I see alkenes and there are two of them, so I'm going to put diene. It's cyclic, so I need cyclo. There are 6 carbons total, so I need hex as my prefix. And my dienes are in the 1,4 position. And then arrange it, you know, in the proper order. That might help you, you know, make sure that you get all the pieces, especially once you start also having substituents hanging off of it. So now we're going to talk about the different classes of polyenes, which is really simple. So there are accumulated double bonds, which means they are stacked on top of each other. So this carbon has a double bond on it, and then the next carbon also has a double bond on it. So double bond, double bond. The trademark of these is that you're going to have these carbons with the linear molecular geometry. So this literally just means that they are right after each other. So you'd have to name it like 1, 2. And again, this is allene. Also, this creates a really interesting geometry. Note that all 4 5 of these atoms are in the same plane. And then these hydrogens are actually perpendicular to these hydrogens instead of being in the same plane. And then there are isolated double bonds. So these are not conjugated because in between them you have an sp3 carbon. So you have sp2, sp2, sp3, which has no unhybridized p orbital, and then these are sp2 again. So this keeps them from being conjugated. There would not be resonance forms of these molecules that would involve this carbon at all. Same with this structure over here. You have 2 sp3 carbons separating your sp2 carbons from each other. And then you have your conjugated double bonds. So in a conjugated double bond, every carbon has an unhybridized p orbital, but you have to have a single bond in between. So this is where they kind of can be confusing between the conjugated double bond and the cumulated double bonds, because they both have double bonds on every carbon. But notice that this carbon here is sp hybridized. It is not sp2. And so it's actually very different from the other ones. So here we have sp2, 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 right? So you have to have that alternating pattern of double, single, double, single, double in order for it to be conjugated. So we have double, single, double, double, single, double. So this part is conjugated, but this part is not part of the conjugated system, which is fine. And then here we have double, single, double, single, double. So this part is a conjugated system, and this carbon is not part of it, which is fine. So that's going to be your difference between conjugated and cumulated double bonds. So we're going to look at the properties and characteristics of a conjugated system, and we're going to use 1,3-butadiene as our example because it is the simplest conjugated system we can observe. So when you're looking at 1,3-butadiene, or any conjugated system really, the sp3 sigma bonds are longer. So what it's talking about here is just a regular sigma bond. None of these atoms are actually sp3 hybridized, but they're saying, in general, say we're looking at butane, sp3 sigma bonds are longer, and sp2 sigma bonds are shorter. And so how that actually comes about on 1,3-butadiene is that the sigma bonds that are actually paired with these pi bonds are a little bit shorter than the sigma bond that is in the middle. Even though it's not actually between two sp3 carbons, since it doesn't have a true pi bond associated with it outside of resonance, it's a little bit longer, but not a lot. Also, we can rotate around the 2,3 carbon-carbon sigma bond. So remember that any single bond has free rotation around it. So if we were to rotate around the single bond, we would end up with this form of the structure, which is still 1,3-butadiene. We haven't really changed anything. But this form is called S-trans, and this form is called S-cis. So the S in this name is indicating that the double bonds are trans to each other with respect to the single bond. So the S stands for single. The S-trans conformation is actually more stable, and this is simply because of sterics. Once it's in the S-cis conformation, it is the least stable of the conformations because we are forcing more electron density to be kind of in the same area, whereas in the S-trans conformation, the electron density is more spread out. So this is just following VSEPR rules, right?